everyone, thank you so much for clicking onto the video. Today we're going to be looking at nomenclature. So we're going to be looking at the different formulas for organic compounds, so empirical, molecular, general, structural, displayed and skeletal. And we're also going to look at the characteristics of a homologous series. And by the end we should be able to draw structural, displayed and skeletal formulas for given organic compounds, apply IUPAC rules for nomenclature to name organic compounds limited to chains and rings with up to 6 carbon atoms each, and to apply IUPAC rules for nomenclature to draw the structure of an organic compound from the IUPAC name limited to chains and rings with up to 6 carbon atoms each. So firstly, we're just going to look at an introduction to organic chemistry. So organic chemistry is concerned with compounds based on carbon, and carbon is special because it forms covalent bonds which allow it to form very long chains, also branch chains and rings. Also, carbon is special as it has a strong carbon-carbon single bond which is non-polar because there's no electronegativity difference between the two carbon atoms. And so first we're going to run through all the different formulae we have for carbon compounds. So the first type of formula we can get is the empirical formula, and this is the simplest whole number ratio of each type of atom present in the compound. So for example, if we had C2H4, which is also ethene, then the empirical formula of C2H4 would be CH2 because we can divide all of the atoms by 2, and so we get the simplest whole number ratio. The molecular formula gives the actual number of each type of atom present in the compound. So for the previous example, the molecular formula would be the C2H4. The general formula gives us the general formula of a functional group. So a functional group is just a reactive group which is attached to a hydrocarbon chain. Hydrocarbon is just something that only has carbon and hydrogen bonds. And so, for example, the general formula of an alkane is CnH2n plus 2, meaning N can be any number 1 and above, CH4 or C2H6. And so you just sub in a number for N. The structural formula shows the arrangement of atoms in a molecule without all the bonds. So here we have a molecule where we've drawn out the entire molecule, and the structural formula is on the right. So we represent it by reading from left to right. So the first one is this CH3, which corresponds to this CH3 here. And then we have CH and then CH3 in brackets. And this is actually a branched part of this molecule. And this is why we put it in brackets. And this CH is here. And then we have CH2 and then finally the OH. The display formula shows all the atoms and bonds in a molecule. So for example, if we have methane, which is CH4, we would draw it out like this, so you can see every single bond. And then the last formula that we can use is the skeletal formula. And in the skeletal formula, we don't show carbon atoms. And so the carbon-carbon bonds are represented as straight lines. So for this example, we have CH3, CH2, CH2, CH3. How we do it is that every single place where the pen changes direction or stops is a carbon. So we assume there's a carbon here, and there's a carbon here, and a carbon here, and a carbon here. And so these are all carbon-carbon bonds. If I draw out this CH3, CH2, CH2, CH3, it'll become a bit more clear. And so we have these 4 carbons, and we have 3 carbon-carbon bonds between them. So how we draw this molecule is first we put the pen on the paper, so this indicates the first carbon, and then we draw a straight line to the next carbon. So this is the first carbon, the second carbon, and then we draw another line indicating the third carbon, and then we have a 4th carbon, and that's where we stop because this chain has 4 carbons. And we also assume that every carbon has the hydrogens attached as well, so we don't draw the hydrogens either. And when it comes to other functional groups such as alcohols, what we do is an alcohol maybe would be OH, like this on the end. And so we would have this shape. We would have this zigzag kind of shape. But at the end, what we would get would be a little tiny line and then OH. So at this end of the tiny line, we don't assume it's a carbon there. It's always the thing which is actually written. So in this case, the OH is attached. It's attached to this carbon here, which is the fourth carbon. So we're going to quickly run through some definitions. The first is a homologous series. So a homologous series is a series of organic compounds that have the same functional group, but with each successive member differing by CH2. So for example, we'll be learning about alkanes. So alkanes have the general formula CnH2n plus 2. So the first alkane we have is methane, and it's CH4. And then the second alkane that we have is ethane, which is C2H6. So it differs by CH2. A functional group is a group of atoms responsible for the characteristic reactions of a compound. So an example of a functional group could be an alkane, or an alkene, or an alcohol. And there's many, many more. An alkyl group is an alkane group that has one less hydrogen. So when we come to look at different molecules, for example, for alkanes, when we have a branched chain, we have an alkyl group attached. The definition of aliphatic is a compound containing carbon and hydrogen joined together in straight chains, branched chains, or non-aromatic rings. The meaning of aromatic is just the name for a compound that contains a benzene ring, and we'll be looking at that quite a lot later in the benzene subtopic. And then the definition for saturated is a species that only has carbon-carbon single bonds, for example, an alkane. And an unsaturated species is a species that has carbon-carbon double bonds or triple bonds, just anything except for only carbon-carbon single bonds. So alkenes have carbon-carbon double bonds, so they'd be classed as unsaturated. Now we're going to have a look at how we name alkanes. So alkanes are a homologous series, which just means that it's a collection of molecules which have this same general formula. And so alkanes have this general formula CnH2n plus 2. They're also regarded as saturated, and that means that they only contain carbon-carbon single bonds. When naming, we use the general prefixes and all the names end in -ane. So the prefixes that we usually use are meth for 1, eth for 2, prop for 3, but for 4, pent for 5, hex for 6, hept for 7, oct for 8, and non for 9, and dec for 10. So what that indicates is how many carbons there are. So meth indicates to you that there's one carbon. And so the N in the general formula of this homologous series will be 1. So that's how we get CH4, because if we put 1 into the general formula of CnH2n plus 2, what we get is C1H2 multiplied by 1 plus 2. So we get the CH4. And so that's methane. And then eth indicates to us that there's 2 carbons. And so you sub in N equals 2 into the general formula, end in -ane because they're all alkanes. Alkanes can have branched chains, and we call these alkyl groups. And these are named by removing the ending -ane and replacing with YL. So methane would become methyl, and ethane would become ethyl. So we're always getting rid of a hydrogen, because if you think about it, so we have a chain that looks like this. If we have a branched group, then this carbon, which is branched, can only have 3 bonds, and so this is why we only have 3 of these hydrogens. Now there are some rules for naming branched chains. So first, what you do is you identify the longest unbranched chain. And it's really important that you remember this. because it's quite easy to just name any of the chains. So you need to identify the longest one, and it has to be unbranched, and then you name after the corresponding alkane like we saw before. And then the chain is numbered to give the branched parts the lowest number possible. And if we have more than one branched chain, we name them in alphabetical order. So for example, we might have a methyl and an ethyl. In that case, we would put the ethyl first because E comes before M in the alphabet. And the last rule is that if we have the same alkyl group on different carbons in the longest unbranched chain, we write both of the numbers separated by a comma and use the prefixes di for 2, tri for 3, tetra for 4, penta for 5, and hexa for 6. So we have two examples here. This first one, the longest unbranched chain is this one here. Or you could have this L-shaped one or this L-shaped one, because it turns out that they're all actually the same length. And so it doesn't really matter. We know no matter what that this is definitely something propane. So we can write that in. We've got a propane here. And then we have a look at the branched bit. So if I'm going to take the straight chain as the longest unbranched chain, we then number the carbons. So I'm going to number 1, 2, and 3. And it turns out also that it doesn't really matter which way I do it, because the branched chain will always be on the second carbon. And so the name of this molecule would be a 2, and then we put a dash. And then because this branch group is a methyl, we then put methyl. So then the whole name is 2-methyl propane. For this next molecule, it's a bit more obvious which one the long chain is, because it's not all the same. So the longest chain is definitely the one which is straight. And so now we can label the carbons. So we have 1, 2, 3, 4, 5, 6, or we could label them as 1, 2, 3, 4, 5, 6. And now we have to work out which one we use. We have to give the branched chains the lowest numbers possible. So in the top scenario with the top numbers, we would have chains on the second carbon and on the fourth carbon. And if we did it the other way around, we would have the branched chains on the third carbon and on the fifth carbon. So that means that we have to go with the top numbers. And so we can get rid of the bottom numbers. And now we count how many carbons we have in the longest chain. So we have 6, so it must be some kind of hexane. The next step we do is look at all the branch chains. So we've got 2 methyls here because they've only got 1 carbon, and we've got an ethyl here. And so the ethyl must go first because it comes first in the alphabet. So that comes on the fourth carbon, so we have 4-ethyl. And then we put another dash, and then we have the methyl groups. So because they come on the second carbon, we put a 2. But because there's 2 of them, we then put a comma and put another 2. And then we have the prefix di, and then they are methyl groups. So the full name of this molecule is 4-ethyl 2,2-dimethyl-hexane. Now we're going to talk about how to name haloalkanes. So haloalkanes are alkanes with one or more hydrogens substituted, which means replaced with a halogen. So there are a few rules for naming. The first is that we name the longest carbon chain again, like the corresponding alkane, and then we use the prefixes fluoro, chloro, bromo, and iodo to indicate which halogen it is, and we also use the prefixes di, tri, and tetra to indicate how many atoms of each halogen are present. And the fourth rule is that we list the different halogens in alphabetical order. So in this example, first of all, we identify the longest carbon chain, which is just a straight one. So we've got 4 carbons, so it must be some kind of butane. So we know that it's a butane and we can put butane at the end. And now we have a look at which halogens we have. So we have a chlorine and an iodine and another iodine. And the next thing we do is we number the carbons. So we could do it like this: 1, 2, 3, 4, or we could do it the other way. So this is carbon 1, 2, 3, and 4. And now we need to remember that the rule is we want the halogens to be on the smallest numbered carbons. And so if we went with the top method, then the halogens would be on carbons 3 and 4. Whereas if we went with the bottom numbers, then the halogens would be on carbon 1 and 2. And so that means that we have to use the bottom method because the numbers of the carbons are lower. And so now we think about which halogen we put first, and the answer to that is the one which comes first in the alphabet. So that would be chloro. So what we have is we have 2, because that's the carbon it's on, and then chloro. And then we put another dash. And now we have the iodos. So we're going to use a 1. And then because we've got 2 of them, we put a comma and then another 1. And then we have to use diiodobutane. And these two words are attached. So the whole name is 2-chloro-1,1-diiodobutane. And now we're going to look at naming cycloalkanes. Cycloalkanes are cyclical alkanes, meaning they're just bonded in a circular way. However, they have a very different general formula. They have the general formula of CnH2n, and we actually come to find that this is the same as alkenes. We name them by using cyclo in front of the prefixes. So it's actually quite easy. So this one has 5 carbons, and so we call it cyclopentane. And you also see why the general formula is CnH2n, because we have 5 carbons and each of them can bond with 2 hydrogens each. And so the number of hydrogens will always be double the number of carbons. Now we're going to look at naming alkenes. So alkenes are another homologous series, and they have the general formula CnH2n. So they're the same as cycloalkanes. And alkenes are described as unsaturated because they contain carbon-carbon double bonds. And so we have a few rules on naming. The first is that we identify the longest carbon chain containing the double bond and name it after the corresponding alkane, and then change the ending from -ane to -ene. And then what we do is number the chain so that the double bond has the lowest number, and we put this number in between the prefix and the ending. So for the first example, our longest chain is this single chain of 2 carbons. And so we must have ethene because we've got 2 carbons, so the prefix is eth, and we change ane to ene, so it would be ethene. And actually, we can just call this ethene because we don't need to put a 1 in, because it can either be 1 or 2, but it needs to be the lowest number, so we put it as 1. But we don't need to put eth1ene because that's the only place it can be in. So if someone told you ethene, this is what you would write down. You don't need to be told where the carbon-carbon double bond is, because there's only 2 carbons. And so that's why we don't actually need a number for this one. However, for the second one, we identify the longest chain. So we've got a chain of 4, so that's the longest chain. And so it's something, it's but something ene. And so now we number the carbons. So we've got 1, 2, 3, and 4, or we have 1, 2, 3, and 4. And so the carbon-carbon double bond is either on the second carbon or the third carbon. It actually doesn't matter which way around we label it, because the molecule is actually symmetrical. And so we can take any of these numbers. So I'm just going to take the top one. And so it needs a 2. So because it's got 4 carbons, we call it but. And then we put a dash. And then the double bond is on the second carbon. So this is but2ene. So this is a general table of how we name our different functional groups. So at the top we have alkane, and they usually always end in ane. And so here we have 4 carbons in the example, so we call it butane. And then we have alkenes, which end in ene. And because in the example we've got 3 carbons, we call this propene. And because there's only one double bond and it's on the first carbon, if we actually put it onto the other carbon, we'll still name it prop-1ene. So we actually don't need any number there. And then for alcohols, we give it the suffix of -ol. So we have propan-1-ol because the OH is on the first carbon, so we have the number 1 there. Sometimes, if other things take priority over the alcohol naming, we use hydroxy as a prefix. And then for halogenoalkanes or haloalkanes, the prefix is chloro, bromo, or iodo, depending on the halogen. And again, we need to put the number in, so that goes before the chloro, the bromo, or the iodo. For aldehydes, which have this COH group, we end with Al. And because in the example we have 2 carbons, it's called ethanol. And we don't need a number because no matter where the COH group is, it'll be the same either way. And then for ketones, which have the CO group, because in the example it's got 3 carbons, so we name that propanone. And then for carboxylic acids, we end with oic acid. So because in the example we've got 2 carbons, we give it the prefix of eth and then put ethanoic acid. And because the example has 2 carbons, we call it ethan and then put oic acid behind it. And then finally for esters, which have the COO group, we give it a YL and then O8. So in the example, what you do is you name the bit without the double bond O first. So that's the methyl. Like when we name chains, we have methyl and then ethanoate is the other 2 carbons. But we'll go into that a bit later. Now we're going to look at some questions. So for question 1, name and give the skeletal and structural formulas for each of these compounds. So first, we can start with the structural formulas because it's probably the easiest. So we read from left to right and we just write what we see basically. So first we have this CH3 group. So we have CH3 and then we have a CH with a branch chain of CH3. So how we write that is we write CH and then in brackets we have CH3. And then we have the same thing. And then CH2 and then CH3. And then for the skeletal formula of it, what we do is we first put the pen to the paper. So this indicates the first carbon. And then we draw a line, and this indicates a carbon-carbon single bond. So where I've stopped is where the next carbon is. So first I'm going to draw out the just the straight chain, so just the 5 carbons. So I've got 2 carbons here, and then draw a line to the 3rd carbon, draw another line to the 4th carbon, and draw another line to the 5th carbon. And then we have methyl branch groups on the 2nd and the 3rd carbons. So this is the 1st carbon here, and so this is the 2nd carbon. So we draw a straight line indicating that there is a methyl group there. And on the 3rd carbon, there's also a methyl group. So this is the structural formula we have for this compound. And now we have to name it. So first we look at the longest chain. So the longest chain is made up of 5 carbons. It's this straight chain. And so it must be some kind of pentane. And then we number the carbons. So we can either number them 1, 2, 3, 4, and 5, or we can number them 1, 2, 3, 4, and 5. And now we need to remember that the branch chains need to have the lowest numbers. And so if we do it with the top numbers, the branches would be on carbon number 2 and carbon number 3. And if we used the numbers at the bottom, the branch chains would be on carbon number 3 and carbon number, and so we have to use the numbers at the top. So we get rid of these numbers at the bottom, and so we know that the branch chains are on 2, and 3. And now we need to work out what the branch chains are. And because they've only got one carbon, that means that they're a methyl group. And this one is also a methyl group. So they're both methyl groups. And so what we do now is we list out the numbers and the methyls. And now we need to also remember to use the prefix because we've got two of the same branch group. So we have to use the prefix di. So the name of this molecule would be 2, 3 with a dash, and then dimethyl pentane indicates the longest chain. So that's telling us that there's 5 carbons in the longest chain. The dimethyl tells us that there's 2 methyl groups. And 2, 3 indicate to us that the methyl groups are on carbons 2 and 3. So now looking at the second molecule, first let's have a look at the structural formula. So what we do is, again, read from left to right. So I'm going to read from bottom left diagonal to the top right. So we have CH3, and then I have CH and then a double bond. So we can write this as CH double bond like this. I know the double bond isn't on the hydrogen, but we can write this for the structural formula. And so we have another carbon, and then we have 2 of these CH3 groups on the carbon. And so we write CH3 and 2. So what that's indicating is that there's 2 CH3 groups attached to the carbon. And this is the structural formula. And now for the skeletal formula. Again, I'm going to start with the longest chain. So it would be the one going diagonally up, the one of 4, or you could have the one which is kind of like a hill as well. It actually doesn't make a difference because they're both the same length. And so I put the pen to the paper, so that's the first carbon, then I draw a line to the next carbon, and then I draw another line to the next carbon, and then another line to the next carbon, because we have 4 carbons in total in the longest chain. And so now that I've drawn that, I'm now going to put in the double bond. So the double bond is between the second and the third carbon. So we have the first carbon here, the second carbon here, and the third carbon here. So the double bond must be here. So this is how we draw it. And then we need to draw the methyl group. So I'm just going to rub out this 3 here. So the methyl group is on the third carbon, and so it comes down here. And this is the skeletal formula for this molecule. Now on to naming it. So we've already identified the longest chain, so we know it's made out of 4 carbons, so it must be some kind of butene. And now we look at the methyl group. So I'm using this as the methyl group. And because this methyl group can either be placed here or on the other carbon and it would still be the same molecule, we don't actually need a number for this methyl, because wherever we put it, it'll be the exact same. The molecule will just be flipped around. And so what we have is we have methyl, and then we have but, and now we have to number the carbons. So we have 1, 2, 3, 4, or we have 1, 2, 3, 4. Now the double bond needs to be on the lowest numbered carbon again, and so it must be 2. So it actually doesn't matter which way we name it, because the carbon-carbon double bond will always be between 2 numbers, no matter if you take the top numbers or the bottom numbers. And so when you choose between 2 and 3, you have to choose the lowest one. So we choose 2. So the name of this molecule is methylbutene. Now moving on to the third molecule, this is a carboxylic acid, and the structural formula for this would be HOOC, so I'm reading it from left to right again, and then we have a CH2, and then a CH, and we have a methyl group attached to that, and then a CH3. So how we read it is that the thing in the brackets, so this, is attached to the carbon which is to the left of it and not to the right. We could, however, also write this OOC, CH2, CH, and then a bracket CH3 and 2, because we can see that there are two of these groups attached to this carbon, but it doesn't actually matter which way we write it. Now moving on to the skeletal formula. Again, we identify the longest chain. So in this case, it would be a chain of 4 carbons. And so again, I'm going to draw the skeletal formula for 4 carbons, which is to the second carbon, to the third carbon, to the fourth carbon. So that's my 4 carbons. And then what I do is on the end of this first carbon, I'm going to attach an OH. And the really important thing to remember is that we don't assume that this is a carbon. We take it as an OH. And so there's no carbon there. And then I also add in the double bond oxygen. So there'll be a double bond oxygen here on the last carbon. And then we also have a methyl group attached to the second last carbon. So we have a methyl group here. And this would be the skeletal formula for this molecule. And now we're going to look to naming it. So we've already identified that the longest chain is 4 carbons, so it's some kind of butanoic acid. And the thing about carboxylic acids is that we always give the double bond O, the carbon with the double bond O and the OH, the number 1, because it's at the end. It's always at the end, so we give it the number 1. And so we label it like 1, 2, 3, 4 like this. And so the methyl group would be on the 3. So the name of this molecule would be 3-methyl butanoic acid. And that's why when we have carboxylic acids, we never have butan 1-oic acid or butan 2-oic acid, because they're always at the end. And it's convention to label that carbon as 1. Before I move on to question 2, feel free to click off the video and try it for yourself first. So draw the display formula of these compounds. For A, draw the display formula of 3-hydroxybutane nitrile. So first what we start off with is we think about the main bit of this compound. And the main bit is the butane nitrile, because hydroxy is just saying that we've got an OH attached somewhere. So the main chain will be the butane nitrile. And but is the prefix for 4. So that means we've got 4 carbons and it's nitrile. And a nitrile is a CN bond. Well, it's when you add a nitrogen to a carbon. And so we have a chain of 4 carbons. And because it's a nitrile, all nitriles that the triple bond carbon N is on the end. And so we have a triple bond to a nitrogen on the last carbon. And so this automatically gets the number 1. So this carbon is the first carbon. And then this is the second, the third, and the fourth. And so this means that because we've got 3-hydroxybutane nitrile, that means that the third carbon is the one which we have the OH on. And now it's really easy to forget that you're drawing the display formula and draw the OH together. But it's really important to remember that for display formula, we need to show every single bond. So you can get marks off if you just write OH. And then we have hydrogens everywhere else. And we don't have a hydrogen on the carbon with the nitrogen attached. For B, diethylamine. So an amine is something with an NH2, but this actually turns out to be a secondary amine. And so what that means is that we have 2 different alkyl groups attached to the nitrogen with the hydrogen attached. And so we have a nitrogen, and then we have two alkyl groups attached, and then that means we only have, so in summary, a primary amine would have a nitrogen and two hydrogens attached. A secondary amine, well, it would also have the alkyl group, and then a secondary amine would be a nitrogen with a hydrogen and two of these R groups, and a tertiary amine would be nitrogen attached to three alkyl groups. And this diethyl amine actually turns out to be a secondary amine. And so we have only one hydrogen, and then we have two ethyl groups. So an ethyl is two carbons, and the rest hydrogens. And this is our molecule for diethyl amine. And then for C, we have 3-bromopropanol. So again, we think about which part is the actual chain. So it's not the 3-bromo because that's just indicating that we're adding a halogen somewhere. So the main bit is the propanol. And propanol is an aldehyde, and so it has the general formula of CHO. And that always goes on the end. And so we have 3 carbons because it's propanol. So we have 3 carbons, and on the last carbon we have a double bond O and a hydrogen. And then we have 3-bromo. So when we have these kinds of functional groups, automatically the carbon with that functional group will be named number 1 because it takes priority. So we have 1, 2, and 3, and so the third carbon is the last carbon, and we've got a bromine attached to it, and then the rest are all hydrogens. And then for D, we have 1,3-dimethyl cyclohexane. So firstly, we draw cyclohexane. So cyclohexane is just 6 carbons, but in a sort of circular shape. So it would be a hexagon because you've got 6 of them. And so we have 1, 2, 3, 4, 4, 5, 6. And these are all bonded together. And then we have 1,3-dimethyl cyclohexane. So that means that on carbons 1 and 3, we both have methyl groups. And it doesn't matter which carbon is 1 and which carbon is 3, as long as you go all the way around naming them 1, 2, 6. So you could have 1, 2, 3, 4, 5, 6. You can start anywhere, it doesn't really matter. And so we have a methyl group. So we have C and then H3. So again, you need to remember to draw every single bond because it's the display formula. And then also on carbon number 3, we also have a methyl group. And then the rest have 2 carbons each, because each carbon can bond 4 times. And that's 1,3-dimethyl cyclohexane.